Hello guys, so we are going to look at the matrix determinant in lecture number 7. Now what a determinant is, it is one of the important aspects in linear algebra, but obviously we are focusing on basically exploring it through Python. Now, obviously I expect you to read about it yourself, but we're going to focus on doing this with Python at the moment using NumPy. So as usual, I'm going to be importing NumPy as MP, matplotlib, and I do the ipython.display for just displaying the nice matrices, and I'm importing simpy as sim. Okay, so that's imported, and I'm going to create this function, the show function, which you have seen before. Now determinant, yeah. Just bear in mind that only square matrices have a determinant, and it's a single number that you can say that it reflects the entire matrix. Now, one important thing to notice is that the determinant of a matrix A would be 0 if there are linearly dependent columns existing in that matrix. In other words, a singular matrix would have a determinant of 0. So you can perhaps, if you have a square matrix and you want to basically quickly find out if it's singular, one way you can tell is to measure its determinant. But yeah, let's go ahead and see how it's calculated. So I'm going to create some symbols A, B, and C and D with using sim.symbols and giving this a string basically A, B, C, D. Okay, so now I have A and B and C and D defined as symbols. And I'm going to create a matrix, yeah? And let me make this bigger. So, and I'm going to create a matrix A using simpy. So sim.matrix A, B, C, D. Okay, let's look at our matrix. Remember, this is a simpy format, and I'm doing it just so that I can show you how it's calculated. Now, when you get a very simple matrix, like a 2 by 2 matrix, it's very easy to calculate the determinant. So you have A, B, C, D, and it's very important that you pay attention to the position of these elements in the matrix, okay? So the determinant of matrix A, which is this, is going to be A multiplied by D, yeah, and then subtract from it B multiplied by C. Well, that's pretty simple. I know you might be like, okay, why would I need a Python to basically calculate that? But of course, we will get to it. So now let's play with numbers. So B equals np.array 2, 3, 5, 1. Okay, so let's look at B. So we have in the rows, we have 2 rows, 2 columns, of course, same size, yeah. So 2 and 3 in the first row, 5 and 1 in the second row. Okay, so as I just said, using this formula, the matrix B would have a determinant of 2 times 1 minus 3 times 5. Okay, so that will give you the determinant of matrix B. Or let's say if you have another matrix, okay, so I'm sure you know it by now. So it's 2 times 9 minus 3 times 6. Very easy, right? Okay. But then, as I said, this seems pretty simple and not really challenging, is it? But when does it get complicated? What if the size of the matrix is larger? So, I mean, think of that matrix, yeah? If I was going to make one like that, following this path, how are you going to do that? Now, let's forget about this. This was just a scare game, you know? So let's just look at a 3 by 3 matrix to start with, and then you will appreciate how complicated it can become very quickly to determine this by hand, when you move from a 2 by 2 to a 3 by 3. So if we have this matrix A, B, C, D, E, F, G, H, I, okay, and let's forget about J, K, L, M, N, O, P, the determinant of this matrix A is going to be this. Okay, how do we come by this? Now, if you pay careful attention here, in the first row we have ABC, second row DEF, and third row GHI. Okay, and I want you to look and think. Yeah. So if you notice, I've picked A from here. That's A, and then there is another determinant associated with these elements, right? Okay. So technically speaking, you are multiplying A by determinant of this section of the matrix. And you're subtracting from it B multiplied, let's look at that, DGFI. Do you see the pattern? DGFI with the determinant of a matrix that would be like these two columns. Plus, you see, suddenly the sign changed. Very important, yeah? This time we have plus. C, which is the last element in the first row, multiplied by the determinant of this matrix or this part of the matrix A. Now, obviously, how do we measure, calculate these determinants? We just discussed it because these are 2 by 2, yeah? So it would be E times I minus HF. That's what would be sitting there. D times I minus FG and D times H minus G times E. Okay. Now let me open a paint, yeah, and maybe that way I can better represent this for you. So I'm just going to copy this image and I'm going to bring this paint over. Okay, so let's copy it. Oh my God, that's a bit too small. No problem. Let's just make it bigger. Maybe a bit that way. All right. So what I want you to realize is that the trend, the way it works is that if you notice, I'm going to like just choose a color. I'll first pick A. This is how the rule works. Yeah. I'll pick A and then it's like I'm ignoring all the other elements in the row that A belongs to and all the elements in the column that A belongs to. Okay, so DG and BC, I'm ignoring them and I'm going with the elements that are not basically shared in the row and vector associated with this A. Okay, so E, F, G. Now when I move to B, so I'm going to just use a different color. Sorry, I really should have had, okay, my bad. Let me just, I do apologize. I'll just do this, so that should be red. Okay, so now I'm going to pick out B and I'm going to use a blue color. Okay, so when I choose a blue color, again, the same rule applies. I'm going to ignore all the elements that are shared in the same row as B, okay, and all the elements that are shared in the same column as B. So in a sense, I'm using these two elements, right? That's how this is working, okay? And the same applies to C. So if I go and pick, let's say green for C, oh, I did that again, didn't I? Okay, so if I go and pick green for C, so obviously I'm gonna ignore all the elements that are in the same row as C and all the elements that are in the same column as C. And it's going to be this section, okay? D, E, G, H, okay? And obviously I would be, calculating this determinant associated with these little matrices that I'm taking out. So that's how you would calculate the determinant of a 3 by 3 matrix. But obviously, when we go to 4, yeah, so that's now you realize why you have these basically, these P's until the last one. So A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P. Okay. Now, pay very careful attention, guys. Yeah. So what's happening here now? Let me just copy this. I'm going to go back to more good old friend, the paint, basically. I'm just going to say file new. Okay. Yeah, don't save it. And I'm going to just expand this. Okay. Oh, we're losing the resolution, but aren't we? Perhaps longer. Okay. Well, cool. Maybe I'll just do this all over again because I felt that it was a bit too basically different. Yeah, maybe that's better. Okay, so if our matrix basically is that, yeah, this is our matrix. It's our matrix. What is its determinant? If our matrix is A, then determinant of A. So if you notice the same rule applies, so we are picking A, all right? We'll do that. We're picking A, and we are ignoring all the elements in the row of A and all the elements in the column that A belongs to. F, G, H, J, K, L, M, N, O, P. Yeah. Sorry, N, O, P on two applies, not M. But don't forget, this is the determinant of this matrix. Okay. Now, calculating the determinant of this matrix, which is a 3 by 3, would require us to go back one step. And if you just recall how we did the 3, how did we do it? We multiplied F by this part of the matrix, then G by these two other two, and H, and so on and so forth. Yeah. So I hope that you follow this. And we are doing a minus plus basically. So as you can see, as the size of the matrices become larger, this will become hideous. It becomes it's not that difficult. I mean, like you see the pattern, but the amount of work you need to do on paper just to do this, and the number of calculations you will need to do is just ginormous. Okay, and you can imagine 5 by 5. How it would follow. I just want you to pay attention to these signs. Yeah, so it always follows a pattern of minus, plus, minus. Okay. Pay very careful attention to that. So this is not really something that you want to do by hand. So it was pretty easy for a 2 by 2, but then when you go 3 by 3, you need to do multiple 2 by 2s. Yeah, so you calculate these just like we did the 2 by 2 and you multiply A. And then when you go to 4 by 4, it just becomes crazy. Okay, so we are not going to do that, obviously. We are going to be doing it using Python, and that's what this course is all about. So, our matrix B. Before, what do we have as the determinant? So B determinant we calculate by hand to be minus 13. And the command is pretty simple. All you need to do is do np.linealg.dtb, and that's it. I mean, as simple as that. So, and you would get exactly minus 13. Let's make a really big matrix, just to challenge Python with it. Yeah, so I'm making a very big matrix because np.random.randint, some random integers from 0 to 20, and I want the size 8 by 8. Now you just saw how complicated a 4 by 4 would lead to, yeah? So just you can imagine what this is going to be. So obviously we are not going to be using pen and paper. We are going to use Python, and I just showed the function to you. So np.linealg.bet, the very big matrix. And if I run that, right away I will get the determinant out in split seconds for something that could have taken you maybe whole day and a lot of headache to go and calculate. Um, I'm just making, this is not, bear in mind, guys, I'm not creating a copy of the very big matrix. I'm not making a copy of the very big matrix, but if you think about it, I'm just making this new matrix equal to a section of this big matrix, but the section happens to be the entire of the matrix, the big matrix. Why am I doing that, guys? Yeah. So just to be sure that, this is not a copy of that. Yeah. You see, if I had done, as a matter of fact, why don't we do it? If I do it like this, yeah, if I do it like this, pay very careful attention to what I did. So very big matrix singular equals very big matrix. If I come and do ID, very big matrix, look at the address in the memory and look at the address of the very big. They are the same, okay? Whereas, if I do it the right way, so I'm going to get rid of, let's just have it there. Whereas if I do this, that I say that this matrix equals, this new matrix equals a section of the very big matrix. Okay, now I have two different matrices. Okay, so if I do ID, which shows you the location in the memory, you can see that now they have different memories. So they are not the same. Yes, they have the same exact elements, but as in defined in the hard disk, they are not the same. So just pay careful attention to that. But then you might be like, Ali, we thought like this is about the determinant. What are we doing? Yeah. It just is that we just calculated the determinant of the very big matrix. Now that matrix was not singular, meaning there was no linear relationship between the columns of this matrix. Okay. So what I'm going to do is look at that. I'm going to say the very big matrix singular, all the rows, yeah, all the rows in first column, all the rows in first column equals the very big matrix, yeah, all the rows in the fourth column to be multiplied by 2. So synthetically, if you can call it, I'm trying to create a singular matrix. Why? Because if I just show this to you, so number all the rows in the column 1. Well, it means like basically this one. Here's 0, 1, 2. So 10 equals number 4. Okay? So number 4, 0, 1, 2, 3, 4. Sorry. 1, 2, 3, 4. So yeah. Let me just do that because, yeah. It's going to be column 4 basically multiplied by 2. Okay? Now, column 4 is 0, 1, 2, 3, 4. Yeah, 5. So multiplied by 2. So in other words, if you see 5, 13, 5, 13, 7, this column and this column are now linearly dependent. Yeah. So this matrix is no longer a single linearly independent matrix. It's linearly dependent, i.e., it's a singular matrix, as I artificially, well, as I just made two of them columns to be linearly independent. Okay, so now I'm going to do np.lineage.determinant of this matrix we created, and what do we get? 0. Sometimes you may not get 0 and you might get some number that goes like 5.6 blah 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 times 10 to the power of minus 9. Yep, that is 0 actually. Yeah, it doesn't mean that your determinant is some really little number. That means its determinant is 0. It's just that due to computing errors, it may not necessarily generate a 0 for you there. Yeah, so just bear in mind. But the idea, I mean, this whole game was to show you that if you have linear dependence in your matrix column space, for example, you are going to have a determinant of 0. Okay? And I've just put that here. Okay? I think in the previous run, when I was preparing this for you, it came out as 9 times 10 to the power minus 9, depending on the random value it was chosen. But that's what I just mentioned, that bear in mind this is 0. Yeah? You don't say that that's my determinant. You really have a 0 determinant there. And something cool, guys, to close the section with. Let's say we have two matrices, matrix A and matrix B, which we just created randomly. Okay, so matrix A, 3 by 3, matrix B, 3 by 3. Those are some random normal distributed numbers. Cool. Now look at this, guys. I'm going to print their determinants, calculate the determinant of each. Yeah, so matrix A has a determinant of -2, and matrix B has a determinant of 1.5 something. Okay, now look at this. I'm doing NP round just for visualize, so that we don't see all these zeros and everything. So if I do a dot product of the two matrices, matrix A and B, yeah, and these 3 basically means round the output up to 3 basically digits, yeah. Let's see what we get. It definitely is not associated, it's not equal to any of the independent, determinants of either A or B. Yeah, so it's a different number. So if two matrices are dot product with each other, there is a new determinant. Obviously, provided that the output, I'm just saying, if there is no linear dependence in there. What if I actually get these two values and multiply them together? So what I'm trying to say is if I get, let me see if I can do that, and multiply it by that. If I run that, -4, 4, 8, 9. Okay, so I hope you understand what's happening. So the dot product of two matrices will lead to another matrix. The determinant of that matrix would equal to the determinant of the first matrix multiplied by the determinant of the second matrix. Yeah, so that's just something cool that I thought I'd show you and close this chapter with. Yeah, okay, so I hope you have enjoyed this, and obviously there is far more to matrix determinants, but in terms of how do you do it in Python, it's as simple as I showed it to you. So if you're interested, definitely have a more read on this. All the best and see you in the next lecture.